Welcome back. In this screencast, we take a look at Euler's method. This is a German name, Euler. It's not Euler. Euler developed this method to help him to numerically approximate solutions to differential equations. And so the best way, in my view, to look at Euler's method is to illustrate it. We'll let dy dx equal x plus y plus 1, and we'll say that y of 1 is 1. Let's use Euler's method with two subintervals to approximate the y value at x equals 1.2. So basically, what happens? Well, here's 1, and figure not drawn to scale, here's 1.2. So we'll take a look at where the curve is at x equals 1. And then we're going to, in Euler's method, we pretend that the tangent line is the curve in a particular interval. We imagine that the tangent line is the curve until some predetermined location. And then we stop and we reconsider and we ride a different piece of tangent line to the solution that we're looking for. So two subintervals means that our first cut point is at 1.1. So we're going to figure out what the slope of the tangent line is at x equals 1. We're going to ride that tangent line to here. Then we're going to figure out where we are, and then we're going to figure out what the slope of the tangent line is at that point, and we're going to ride a different piece of tangent line to x equals 1.2, and whatever this y value is will be our approximate y value at x equals 1.2. But how does that work? Well, at this point, this is the point 1, 1, the slope of the tangent line is 1 plus 1 plus 1. The slope of the tangent line is 3. And then we do 9th grade slope. We know that slope is rise over run. It's delta y over delta x, except that we know what delta x is because we know how far it is from 1 to 1.1. So we know that the slope of the tangent line is change in y over change in x, which means that the change in y on the red tangent line is 0.3. Which means that the coordinates of this point that is so valuable in our recalculation, well, we know the x coordinate's 1.1, and we know the y coordinate is the previous y plus the change in y, like so. So y of 1.1 is approximately the previous y plus the change in y, that's 1.3. And then second verse, same as the first. We figure out what the slope of this line is. And the slope of this tangent line is the x value plus the y value plus 1. 1.1 plus 1.3 plus 1. That's that's not. That's 3.4. Ha ha ha. And that slope is a change in y over a change in x, which means that the change in y on the blue slope triangle is 0.34, which means that the y value at 1.2 is approximately the previous y value plus the change in y. And this is Euler's method for approximating a numerical solution to a differential equation. We use the derivative to find the slope of a line, and then we pretend that the function is the line because the interval is small enough. Then we do a little bit of 9th grade slope, and we add on, and we're done. I should probably do one more of those. It's probably wise. suppose dy dx is x minus y, and let's again let the function pass through 1, 1, use two equal subintervals to approximate the y value at 2. The y value at 2. So we start the function at 1, 1. We figure out what the slope is at 1. We work our way to halfway, and then we figure out what the slope is there. At the point 1, 1, the slope of the tangent line is 0. Well, that's easy. If the slope of the tangent line is 0, then 0 is change in y over change in x. I think I can do that, which means that the y value at our first rest stop is the previous y value plus the change in y. That's pretty good. So the coordinates of this point are 1.5, comma 1. Now we've got to figure out what the slope of the tangent line is at 1.5, comma 1. Well, the slope of the tangent line is the x value minus the y value, which means that the slope of the tangent line in this stretch is 1/2. And that slope is a change in y over a change in x. That slope is a change in y over a change in x, which means that the change in y is 0.25. And that means that the approximate y value at 2 is the previous y value plus the change in y, and that's 1.25. That's a numerical approximation for a solution to a differential equation. It helps us see the curve as a bunch of tiny pieces of tangent line. I hope this is helpful. We'll see you soon.